Hello and welcome to video 6. This one is regarding two-dimensional methods like HSQC and HMBC to establish proton to carbon correlations via different bonds, bond lengths, or distances. And it's actually a continuation from video 3, which was on depth. And in that video, if you recall, we were able to only unambiguously identify 4 carbons. We could make guesses on the others. So even for a simple molecule like ipsenol, we saw that we can establish the structure, but as far as being able to exactly identify which atom is which, we needed more data. So I hadn't shown the Proton NMR for ipsenol. Here it is. I don't know why they use Hertz values on these, but these are expansions of all the individual signals in the spectrum. And what I've gone ahead and done is made a table of the proton assignments. So just pointing out a few features, we've got what looks like an apparent triplet that integrates for 6 hydrogens. So it seems like that's a 2-methyl triplet signal. And then other things like here, it's tempting to call that a septet, but actually knowing what I end up knowing in the end, it's probably, I went ahead and just called it a multiplet. There's a little bit of ambiguity there as to what's going on. Otherwise, we have some highly split signals distributed throughout the spectrum, and we see the structure already. The signals here are the ones here at between 5 and 5.3, 5.2, and I've just labeled those all together as integrating for 4 hydrogens. I don't know exactly what we're seeing here, and maybe we'll be able to figure that out in the end. So I made my table of proton values and integrations. From the depth, as before I mentioned, we had identified these 4 mostly by virtue of one of them being quaternary and not showing up in the other depth spectra, and then one being extremely de-shielded, C7, so right there, identified, the only alkenyl CH in the molecule, having the structure. C6 is the quaternary, C4 and C2, here and here, are easily distinguished. One, because C4 is attached to the OH, so that's going to be really de-shielded. Those are always around 70. All right, so we have that so far from depth. Now we go on to HSQC, and I've gone ahead and made a table showing the carbon signals, what multiplicities they are in depth, and then I've gone ahead and filled in what correlates to what in the HSQC. Actually, this was an earlier version called HMQC, but this is really sharp data for HMQC. And things that we can point out, for example, is still back to this signal at 5 to 5.2. Notice there's a left and a right side of it. Left, right. And they correlate to these 2 signals at 114 and 118 in the carbon NMR. The correlations end up so that you can designate right side and both sides. See, the 114 actually correlates to both sides, what I'm calling both sides of this 5.0 to 5.2 signal. So that's a strategy you can use. You may never even resolve these, but it's still valid if you see distinct cross peaks like that. The other thing that is revealed by HMQC is that if you were to expand on these 2 methyls, they actually correlate to different carbons, 22 and 23, only 1 ppm apart, but still distinguishable. And so in fact, it appears as though what we thought was a triplet was in fact a doublet and another doublet overlapping so that it appeared to be a triplet because of overlap in the middle. So it's actually a pair of doublets very tight together. We can make use of these assignments in HSQC, kind of, if you recall the Zoom session last night, in fact, where we can walk our way through the molecule finally using HMBC. So where we're at now after HSQC is here, and so the only ambiguity left is circled in red. We have these two protons and that carbon, these two protons and that carbon, and then which carbon is which as far as this carbon here, if you're seeing, and this carbon here, we don't yet know. So what we need to distinguish these two carbons is really clarification on this methylene right here. Notice the protons here at 6.4 would see both, so that's not helpful. But these protons here would see 1, 2, 3 bonds away to this one, and this carbon over here is much too far away to see any correlation. So we need to know what this is. The best way to really for sure say is to see if there are correlations from the 1.80 or from these methyls to this carbon right here, with the upper carbon up here being too far away. So you can go into the HMBC directly, although I would still recommend tabulating all these first, because you may not have this convenience. But the 1.80 signal is right here. It's highly split, and it goes and correlates down to the 46, not the 41. So right there we have a 1-2 bond correlation, and we can basically say that that's 46. If we look at correlations from the methyls, we see the same thing here. Both methyls correlating to the 46 and not to the 41. So that's this correlation here, this correlation here. So we've pretty much confirmed without a shadow of doubt that this carbon is 46. This carbon necessarily is 41. And we know what protons are attached to those from HSQC. The protons on 41 are going to be, again, key to looking over in this direction. So let's go down to what the HMBC has brought us. We're here. The 2.48, 2.21 are what are attached to 41, and I've gone ahead and filled in the 1.31 and 1.45 as well. We're looking for correlations from here to here. 2.48 to 2.21, going back up, are these two signals here at the very top. They correlate down to, notice, both of them to 118 and not to 114, is it? So that basically shows us that this carbon here is delta 118, this carbon here is delta 114, and now we have every single atom assigned except for this weirdness between 5.15, 5.20, and we can try to explain what that signal is. So that signal, knowing the structure, let's go back up here. Knowing the structure, we would expect one of these protons to be a doublet, coupling to this one right here. This should be a doublet, also coupling to that one. This one should be a doublet of doublets. So we predict doublet, doublet of doublets. And then here we would kind of expect basically a singlet. But if there's further coupling between these two, geminal coupling, then maybe a doublet. So we have some kind of signal at the top that's all of these overlapped. Perhaps a doublet of doublets, another doublet, and another doublet with a different magnitude of splitting. I should probably fix that. So like a narrower and a wider split where we have these as trans and cis. Little tip there. So trans alkene protons have broader or stronger coupling. So if we go and try to overlap all these to create a signal that looks like what appears above, we might see a doublet and another doublet of doublets overlapping, and then maybe another couple of doublets overlapping. And it's not hard to imagine that if you connect all these, that you end up with some sort of signal that looks like what we're seeing, with overlap on all of these 3 ones on the end. So that would be my explanation for that. So what I would say is to further get practice, go ahead and fill out this, pardon the video, fill out this table that's attached to, that's posted as a document in the material for this YouTube video on Canvas. That's what I meant to say. So you can go ahead and just for practice fill these all in. Then once they're filled in, go back and make sure they make sense given the structure we're seeing. All right. And that brings us to the end of this video. Thanks.